Hello everyone, I want to welcome you to another section on UV spectroscopy. In this video, I'll be talking specifically about terms used in Woodward Fieser's rule. In the last video, I explained what Woodward Fieser's rule implies. I said it is a set of rules that is used in determining the maximum absorption wavelength of any given compound, most times that has conjugated double bonds. So in this video, I will be talking about different terms that are very important that we need to know in using Woodward Fieser's rule in getting the maximum absorption wavelength of any compound given to us. And first, like I said, the concern is about conjugated system, or let me say conjugated double bonds, whereby you have two double bonds that are separated by a single bond. So first, talking about conjugated system, a conjugated double bond can be present in an acyclic system and can also be present in a cyclic system. For example, I could have this and I can also have this. At the same time, I can also have something like this. This is acyclic and this is cyclic diene, and this is an acyclic diene. Now, the double bond in each of these systems are separated by a single bond. For example, in this one, this is a double bond, and a single bond in between them. This is a double bond, and a single bond between them. This is a double bond, and a single bond between them. So each of them has two double bonds separated by a single, separated by a single bond, which makes it a conjugated system. But where the two double bonds, where the conjugated system is different, the conjugated system here is in an acyclic system, while in this two it is in a cyclic system. At the same time, for conjugated double bonds in a cyclic system, you can have the two double bonds to be in the same ring, and you can have the two double bonds to be in different ring, and that's what makes the difference between this. So for this, whereby you have the two double bonds to be in the same ring, you say that's an homoannular diene. Homoannular diene. But for a system like this, whereby the two conjugated double bonds are in different rings, you said it is heteroannular diene. Now, another thing to also take note is what we call exocyclic double bonds. Exocyclic double bonds are double bonds that are directly attached to the ring system. So most times they apply to conjugated double bonds that are present that are within a cyclic system, a ring system. So, and in that case, like I said, exocyclic double bonds are double bonds that are directly attached to the ring system. For example, I have this. Now, if you look at this particular compound, this particular system, we have a conjugated double bond there, which is this double bond and this double bond, which are separated by a single bond. But this double bond that is outside there is directly attached to this ring at this point. So that makes this double bond an exocyclic double bond. Another example is also the way you have something of this nature. Now, in this system too, we also have a conjugated system whereby we are having this double bond and this double bond separated by a single bond. But first, like I said, the two double bonds, one is outside, one is within the ring. That makes it an heteroannular diene because they are not within the same ring. But at the same time, because this double bond here is directly attached to this ring on this side, at the same time directly attached to this ring, that makes it a what? That also makes the double bond an exocyclic. So this system as it were has one isocyclic double bond, while this has two isocyclic double bond. So that's different. So we can always have a double bond that is directly attached to a ring system, and such double bonds are called isocyclic double bond. Another important term that we also have to take note is what we call double bond extending conjugations. Now, this occurs when you have more than two conjugated double bonds. For example, I have three double bonds that are conjugated together. If I have four double bonds that are conjugated together. So in that kind of system, I will have another term that we call double bond extending conjugation. For example, if I have a system like this, or if I have, let's say I have these two. Now, in this system that we have now, these two, so in this case now we have like three double bond conjugated together. This is the first double bond, the second double bond, and the third double bond. If you look at this system now, you'll see that each of the double bonds are separated by a single bond. If I should trace it out for us, for example, like this, we have something like this. So this is the conjugated system that involves three double bonds, and that involves three double bonds which are separated by a single bond. But where double bond extending conjugation comes into play is that two of the double bonds will be like your basic chromophore, while the other one will be an extension of the basic conjugated double bonds. So in the sense that these two that are in the same ring, that will be your basic chromophore, the part of the molecule that is absorbing the UV light, While this one also is also part of the conjugated system, but it is an extension of these basic two. So we call that a double bond extending conjugation. In this case too, I can also trace out the conjugated system, which involves three bonds. So we have this. So this is the conjugated system. But the conjugated system, like I also said, involves three bonds which are separated by a single bond. So what we're trying to say there is that in this case also, because I'm having more than two conjugated double bonds, that implies that one of them will be a double bond extending conjugation. So in a case whereby you have more than two conjugated double bonds, we always have a double bond extending conjugation. Let me also give another example. Let's say we have this. Now, in a system as this, like I've done here, we have like four double bonds that are conjugated together. So I have this. If I should trace that out, I will have something like this. So the conjugated system here, the whole system has four double bonds. This is a double bond, followed by a single bond, a double bond followed by a single bond, a double bond followed by a single bond, and then a double bond. So we have four conjugated double bonds. So, but in this case, like I said, two of the four will be like your basic chromophore, while the other two will be double bonds extending the conjugation. So in this case now, the two double bonds within the same ring will be like your basic chromophore. So you can say this double bond is a double bond extending conjugation, and this also is a double bond extending conjugation. So this system here, we have two double bond, DB means double bond, extending extending conjugation. While these two examples I made here, they both have one double bond extending conjugation. And the last term I want to talk about is the what we call ring residue or alkyl substituents. Now, most times we also consider sp3 carbons, that is sp3 hybridized carbon, that are attached to the conjugated system, and we tag them to either be a ring residue if the sp3 hybridized carbon is part of the ring, or we also call them we also call them alkyl substituents if the sp3 hybridized carbon is not part of the ring. For example, let me probably use the ones that we already have on the board. In this particular system here, whereby we have conjugated double bonds, we have two conjugated double bonds. If I'm to find the number of ring residue in this case now, that would be, now the first thing I would suggest to do is to trace out your conjugated system, which is this. In this case, this is the conjugated system. So you now look at the sp3 carbons which are directly joined to this particular system. One is this carbon here is joined to this system here, and that's the first ring residue. This carbon here also is an sp3 carbon joined to this system, and it's also a ring residue. So in this system, as we can say we have two ring residue. We have two ring residue. Let's consider these two as an example. If I trace out the conjugated system, that would be this. That's the conjugated system. So how many ring residue are we going to have in this case? That would be this, a carbon, an sp3 carbon attached to this at this point. So that's one. This is also an sp3 carbon attached to this system here. That's one. That's two. And also this carbon here is also an sp3 carbon attached to the system. That's three. So here we are going to have three ring residue. Now another one, let's also use this as an example. So I can also have, so if I also trace out the conjugated system here, that would be this. So you trace out where you have your conjugated system. So let's identify the ring residue. This is the first carbon here that's attached here. We have second one here. We have the third one here, and we have the fourth one here. So that means this one has 4 ring residue. R means ring residue. Now, but to probably point out the alkyl substituent, like I said, these are also sp3 carbon attached directly to the conjugated system, but they are not part of the ring. Let me give an example. I have something like this. I have this. I have this. I have this. So this is an example of a compound with an alkyl attachment, which is CH3. So if I want to identify the chromophore here would be what? To be this. The conjugated system here will be this. This will be the conjugated system because this is double bond separated by a single bond. Now, because there is just two double bonds that are conjugated together, we don't have double bond extending conjugation. Another thing that I can also take note from this place is that this double bond here is directly attached to this ring at this point. So you can say that this double bond is an isocyclic double bond. But going back to what I'm talking about, which is ring residue and alkyl substituent. So let's look at sp3 carbon that are directly attached to the conjugated system. One is this carbon at this point. The second is this at this point. The third is this at this point. But this one that we have, which is let me probably write that as CH3, is an alkyl. It's an sp3 carbon here that's also directly attached to this conjugated system. So we also have, so here we are having like 3 ring residue and 1 alkyl substituent. So we have 3 ring residue and 1 alkyl substituent. So we have that. But in most times, or let me say sometimes, some people use these two words, they use them interchangeably. they can use them, you can hear them saying ring residue, you can hear them saying alkyl substituent. But that's the difference. When you have sp3 carbon that are directly attached to the conjugate system, then you have your ring residue or your alkyl substituent. If the sp3 hybridized carbon is part of the ring, then you call it the ring residue. But if it's not part of the ring, then you call it your what's it called? We call it an alkyl substituent. And now, but it is not every alkyl substituent that you consider when trying to use your Woodward Fieser's rule to get the maximum absorption wavelength. For example, if I have this compound, I have this structure, I have this, I have this, I have this, and then I have this piece. So this is an alkyl substituent, your CH3, this also is a alkyl substituent. So, but the point here, if I check out the conjugated system now, that will be this. This is the conjugated system there. So now what are the ring residues? This is the first carbon, sp3 carbon attached to the conjugated system at this point. You also have one carbon here attached at this point. This is another sp3 carbon attached at this point. This is a CH3, an alkyl. That's our methyl. It's also attached to the what? To this conjugated system here. So we have this. So we are having like 3 ring residue and 1 alkyl substituent. But this also is an alkyl attachment, which is your CH3. But we don't consider this alkyl because it is not directly attached to the conjugated system. So most times when you are trying to calculate maximum absorption wavelength, you consider only attachments, or yes, you will consider only substituents that are directly attached to the conjugation system. If the substituent is not directly attached to the conjugation system, you don't consider it. There are other attachments that we also use that can also be part of any compound, or let me say any conjugation system that is given to us. But we are going to talk much about that in the subsequent video. So in this video, we have tried to introduce us to several terms that we also have to know, or that are also very important for us in using Woodward Fieser's rule, starting from the acyclic diene, which is when you have conjugated system in an acyclic system. We also have cyclic diene, which can either be homoannular or heteroannular. That is when you have two conjugated double bond within a ring system, which can either be within the same ring or in 2 different rings. We've also talked about exocyclic double bond, which are double bonds that are directly attached to the conjugate to a ring. When you have a double bond that is directly attached to a ring system, then you call it an exocyclic double bond. I want to talk about double bond extending conjugation, which I said applies to conjugated system with more than 2 double bonds. So whenever you have a conjugated system that has more than 2, then you can always have a double bond, or you can always have double bond extending conjugation, which can either be 1, it can be 2, or even more. And the last thing I talked about is the ring residue and the alkyl substituent. The ring residue, like I said, they are sp3 hybridized carbon that are part of the ring system, and they are directly attached to the conjugation system. While alkyl substituents, they are also sp3 hybridized carbon that are not part of the ring, but they are directly attached to the conjugation system. And I also said that it is only substituents that are directly attached to the conjugation system that you consider in calculating your Woodward, in calculating the maximum absorption wavelength. And we also have to note that maximum absorption wavelength calculated using Woodward Fieser's rule has an error of plus or minus 5 in case we encounter anything like that. So most times when you do your calculations using Woodward Fieser's rule in calculating the maximum absorption wavelength, the error of your calculated value is plus or minus 5. At this point, I want to say thank you for watching this video, which is another section on Woodward Fieser's rule. So in the subsequent video, we are going to be looking at two classes of compounds which I mentioned in the previous video, which are the conjugated diene compounds and also the unsaturated alpha beta carbonyl compound, which are the basic two classes of compound to which we can apply the Woodward Fieser's rule. But this is just to introduce us to several terms that we need to probably get familiar with before entering into another topic under Woodward Fieser's rule. And I hope and I believe that you have get one or two things from this video. I hope that you will continue to watch the videos, at the same time introduce it to your friends which might also be in need of these lessons. And you can do well to not just watch, but at the same time like and subscribe. And if you have any comments or questions for me, you can certainly drop it in the comments section. I would be glad to reply to your questions on anything that we have talked about in the video. Thank you.